solve this.
These videos can be useful. They allow a more direct contact with the matter, allow to pause and review, but they do not dispense with counseling with the teacher, as they may contain errors, which, if they are found, thank you for communicating. Furthermore, in logic, there are sometimes different ways of saying and doing. If that's the case, they also have the option to mute the sound.
Round 1.
Logic is not a difficult subject. It is a complex subject, but it is not difficult. It requires study and training. In logic, you learn gradually, almost like in a computer game. When we learn the essentials of a certain level, we are able to proceed. Later, when we look at initial levels, they do not present any difficulty. In today's video, we are going to do one more demonstration, a formal proof. In the first premise, we have a conditional. If P, then Q. In the second premise, also a conditional. If Q, then R. This argument is a little more complex. It has 4 premises. Thus, in the third premise, we also have a conditional, if S then T. And in the fourth premise, a disjunction, P or S. At the conclusion, we have a disjunction, R or T. We start the proof and write. On line 1, if P, then Q. On line 2, if Q, then R. On line 3, if S, then T. On line 4, P or S. After indicating the premises, we look at the conclusion. We have the disjunction R or T. We know that is what we have to prove. That which, for the argument to be valid, must be derived from the premises. As you remember, we are going to change the formulas that represent the premises by applying rules of inference, or by replacing them with equivalent formulas. So, in the end, we arrive at the formula we have in the conclusion. We look at the set of formulas that represent the argument up at the top of the chart, the conditionals that we have in the second premise and in the third premise contain in their consequence R and T, respectively. We will need R and T to prove the conclusion, but if we can't extract them from the conditionals in which they are inserted, they are of little use. But maybe it's possible. Notice that we don't have any isolated formula that allows us to confirm any of the conditionals, nor any conjunction that would allow by itself to obtain isolated formulas, and thus confirm any of the conditionals. We have a disjunction in the fourth premise, but the disjunction alone does not allow for isolated formulas. We know that for a disjunction to be true, it it is enough that one of its terms is true. Thus, we know that in the fourth premises, P or S is a true disjunction. If it is not preceded by the negation symbol, it is true. But we don't know which of its terms is true, or whether both are true. All we know is that they are not both false. Thus, starting only from the disjunction P or S, we cannot infer neither P nor S separately. If it was a conjunction, we could do it, as we have seen in the previous videos.
At first glance, there is no way out.
Wrong move.
We then try to see if there is anything we can do with the premises we have. If there are any rules of inference or remarkable equivalence that can be applied, then any change that we can make could be a way to prove the conclusion. With the first and the second premises, we can do anything. If we have two conditionals in which the consequent of the first is the antecedent of the second, we can infer the antecedent of the first implied in the consequent of the second. Applying the rule of inference, hypothetical syllogism, as remembered. Thus, in the first line of the proof, we have a conditional that reproduces the conditional of the first premise. In the second line, we have a conditional that reproduces the conditional of the second premise of the rule. In this example, the letters we use in the demonstration and the ones we use in the rule coincide. Obviously, they could be different letters. Thus, as the rule allows, we can conclude a conditional in which we have the antecedent of the first conditional to imply the consequent of the second conditional. We then obtain if P then R, and we write in the fifth line of the proof, indicating lines 1 and 2 as being the lines that allow us to take this step, and justify this step with the rule of inference, hypothetical syllogism. Looking at the argument at the top of the table, so at first glance we can't get R starting from Q. There's nothing to confirm Q. If you notice the disjunction we have in the fourth premises, we have P. And not only do we have P, we also have S, which can confirm the conditional if S then T. We will be able to confirm both conditionals. In order to be able to apply this rule, we will still have to apply another rule first. So let's aggregate the two conditionals through a conjunction. So if P then R conditional of line 5 of our proof is in the position where we have P, in the first premises of the conjunction rule of inference. The if S then T conditional from line 3 of our proof is in the position where we have Q, in the second premises of the rule. We can then obtain the conjunction if P then R and if S then T. We write in line 6 of our proof, indicate lines 5 and 3 as being the lines that allow us to take this step, and justify this step with the rule of inference conjunction. To finally reach the conclusion, let's then apply the constructive dilemma inference rule, which is a rule that says that if we have a conjunction between two conditionals and we have a disjunction whose terms are the confirmation of the antecedents of the two conditionals, we can conclude a disjunction whose terms are the consequence of the two conditionals. Thus, in line 6 of our proof, the conjunction if P then R and if S then T is in the position of the first premises, which we can observe in the constructive dilemma inference rule. Line 4 of our proof, the disjunction P or S is in the position of the second premises, and we can conclude in line 7 of our proof the disjunction R or T, which is in the position where we have the conclusion in the rule. The constructive dilemma is an inference rule that excels in ingenuity. Note that the constructive dilemma is a rule that is based on a double modus ponens.
Wrong 3.
If we split the rule in half, what do we get? We have a double modus ponens. Note that the conditional of line 6 of our proof, if P then R, is in the position of the first premises of the modus ponens rule of inference. On line 4 of the proof, P is in the position of the second premises of the modus ponens. And on line 7, R is in the position of the conclusion of the modus ponens rule of inference. Analyzing the second half of the constructive dilemma rule, we also have the modus ponens applied to the second conditional of the rule. Thus, in the sixth line of our proof, the if S then T conditional is in the position of the first premises of the modus ponens rule. On line 4 of the proof, S is in the position of the second premises of the modus ponens. And on line 7, T is in the position of completion of the modus ponens rule. The constructive dilemma is based on the dual application of the modus ponens rule. But not only that, it also contains a conjunction and a disjunction. In terms of the disjunction, it contains confirmation for the antecedents of the two conditionals that are joined by a conjunction. And then, what is that the information contained in the two premises of the rule allows to conclude. Obviously, what allows us to conclude is also a disjunction, whose terms are the consequence of the two conditionals. If, in the second premises of the rule, we confirm the antecedents of the two conditionals, then we can conclude, or rather, all that we can conclude are the consequence of the two conditionals aggregated by means of a disjunction. And I say everything because the disjunction P or R of the second premise of the rule does not allow to confirm the conditionals separately, for it only asserts that one of its terms is true, leaving open the possibility that both are true, while guaranteeing that they are not both false. Thus, we can conclude the two consequences of the two conditionals also aggregated by means of a disjunction. The conclusion is telling us that it is enough for one of the two to be verified for the argument to be valid. When the stair light comes on in a building, we know that at least one of the switches has been activated, without knowing for sure which one or which ones. And we verify a practical application of this rule. Thus, in line 7 of our proof, we write R or T. We indicate lines 6 and 4 as the lines that allow us to take this step, and justify the step with the constructive dilemma inference rule. Once again, we were able to design a structure with the formulas contained in the premises that allow us to state that this argument is a valid argument, since the conclusion follows from the premises. It derives from them. See you again in next video. Greetings.
Hey yo, I'll be back. Hey yo, I'll be back. I'll be back.